Hey guys, I want to talk to you about polynomial and rational inequalities. Actually, that's 8.4, but I'm just going to talk about rational inequalities only. It's the harder of the two, and so I think it'd be good just to make a video about it. Everything that I say applies to polynomial inequalities. There's just a little bit less to do because rational inequalities have a few more options. So a rational inequality is exactly that, an inequality with a rational expression in it. So something like 7 over x minus 1 has to be less than 5. Now, there's a lot of problems when we start dealing with inequalities. We know that we could fraction bust whenever we have equations or inequalities, but the problem is that I can't really fraction bust because I don't know if x is positive or negative. Like if x is a big enough positive, then there's no problem fraction busting. But if x is a negative number, then I have to flip the inequality, and so I can't really do that while I have a rational inequality. Now, what is this question really asking me? It's asking me to find the x value so that 7 over x minus 1 is less than 5. I want to show you for a second what that looks like. Graphically, I can input 7 over x minus 1. It looks like this. This is the graph of a rational function. It has a vertical asymptote and a horizontal asymptote. It never gets crossed. And so what this question is asking me is, when is this rational function actually less than 5? So if I graph the line y equals 5 also, you see that, y equals 5. You see that, okay, this line is kind of the cutoff. I see that the rational function is above 5 on all of these x values. So like if I maybe just, I don't know which tool I could use necessarily, but if I know that from here on, all of the x values less than 3 but bigger than 1, or less than 2.5 or whatever this is, all of these x values from here to the left up till only to 1 are between these 2 points are the x values where the graph is greater than 1. So everywhere else the graph is greater than 5. Everywhere else the graph is below 5. And so that's what this question is asking us. When is this 7 over x minus 1 actually below 5? When is it less than 5? Well, the truth is that, but if you're not going to graph it and look at it graphically and see where it's above 5 and where it's below 5, then the next best way is to do it algebraically. And so the truth is that you need to find two things. You need to find the point where it actually touches 5, and you need to find any vertical asymptote. And what I'm telling you is the vertical asymptote is 1. Because if I at least know these two x values, then I could test something to the left, I could test something to the right, and I could test something in between and just plug in values. Because if it's below this value to the left, then it's going to stay below forever, because otherwise I would have had another point, like maybe over here, where the graph touched this line. So I'm saying this graph is below the line 5 up to the point where there's a vertical asymptote. And then after that, it could be above or below. In this case, it's above until it touches it again. After that, I see that it's below, and it's going to stay below for the rest of forever, because that's the only time that it touches the line 5. So if I just keep zooming out, you see that, yeah, everywhere else, it's below the graph except for that one little sliver that we had before between these 2 points that I'm calling A and B. So graphically, that's what's happening. I want to find the values where this function is less than 5. Okay, but what I'm telling you is you need to find those 2 points. I like to call them boundary points. They're the x values that where 1, there's a vertical asymptote. There's a vertical asymptote whenever 7 over x minus 1 is undefined. Well, 7 over x minus 1 is undefined when x minus 1 equals 0. So if I add 1 when x equals 1. That's why graphically there's a vertical asymptote here at 1. You can't see it. It's an imaginary line, right? But then I also want to know, when is 7 over x minus 1 equal to 5. I like to call these the roots. The question doesn't say equals, but I'm saying find that one point where you actually get 5. Find this value right here, this x value, so that you can solve it as well. And so what do? You just set 7 over x minus 1 equal to 5 and fraction bust. The nice thing is that now I have an equation I could fraction bust. I couldn't do it with an inequality, but with an equation, that's no problem. I can multiply both sides by x minus 1, and everything works out nicely. So let me maybe do it over here. If I have 7 over x minus 1 equal to 5, I multiply by x minus 1 to cancel that x minus 1 out. And that gives me 7 equals 5x minus 5. So that if I add the 5 over, I get 12 equals 5x. And if I divide by 5, I get x equals 12 over 5. 2 2/5. That's the x value. 2 2/5 is exactly where the graph touches the line. And so you can do this algebraically without the graph. That's what we're working towards. But what I'm telling you is you need to find these special points wherever there are vertical asymptotes and wherever the actual equation is, wherever the inequality is actually equal to the other side. Again, you could only fraction bust here because it's an equation. If I go back up to the inequality, I don't know whether x is positive or negative. X could be any value, so I can't actually fraction bust at the original equation, right? So I have to change it to fraction bust, but now that I have an equation and I found that value, I got to go back to the inequality. So how can I figure out algebraically where the graph is actually greater than 5? I should make a table. I should plug in values to the left of 1, to the left of 12 over 5, but still in between 1, and then to the right of 12 over 5. So like this is the interval from negative infinity to 1. This is the interval from 1 to 12 over 5. This is the interval from 12 over 5 to infinity. I just got to choose a number in that interval on the interior of the interval, so something like x equals 0, something like x equals 2, something like x equals 3. These are all good values in their respective intervals to plug in. Where do I plug them into? I plug them back into the original inequality. I just want to know, basically, I just want to know if to the left, if I pull up the graph, to the left of 1, is it below? To the right of 1, but in between 12.5, is it above? And to the right of 12.5, or 12 fifths, sorry, 2 2/5, 12 fifths. If to the right of 12 fifths, it's below the line also. So if I plug in 0 into the original, I want to know, is 7 over 0 minus 1 actually less than 5? Now graphically we know that this worked, but here's why. 0 minus 1 is negative 1. 7 divided by negative 1 is less than 5. So it works. That is a good interval. So I know that everywhere from negative infinity up to 1, my graph is below 5. Now we also knew that in between the interval 1, in between 1 and 12 fifths, it didn't work. Again, if I take 7 over 2 minus 1, I want to know if that's less than 5. Right? I'm just plugging it back into the original and seeing whether it works. Well, in this case, 7 over 2, 2 minus 1 is 7 over 1, and that is not less than 5, so it does not work. And graphically, I see that, yeah, of course, everywhere between those, the graph was above the line. Now for x equals 3, I plug it in. 7 over 3 minus 1 becomes, is that less than 5? Well, 7 over 2 is definitely less than 5. That's just 3.5, so it works as well. That means then that the solution set is the interval from negative infinity up to 1, unioned with 12 fifths to infinity. And again, graphically, that's showing you, telling you the intervals, the x values, where the graph is below the line 5 and where it's above the line 5. Everywhere to the left of 1 and everywhere to the right of 12 fifths. The interval from negative infinity to 1, union with 12/5 to infinity. So the idea is that there's 4 main steps that you can follow. You should always first find the vertical asymptotes and the roots. So I'll just say find the boundary points. And again, I'm just calling it the boundary points because that's the point where the two intersect. These are the two boundaries of the table that I'm going to make. They are vertical asymptotes and roots. The roots come from when you just change the inequality to an equal sign. Once you find those, make a table and test values. Just like we did before, we're testing values to the left, to the right, and in between those ones that we found, the boundary points. And then definitely the third thing you should do is write your answer in interval notation. So let's say, for example, that I was asked to solve something like (5 over x minus 2 less than 1). Again, this inequality is asking me where's the graph less than 1, but I'm not even going to bring up the graphs. What I'm telling you is that first, you should find the vertical asymptotes. The vertical asymptotes always occur wherever the denominator of the rational expression equals 0. So wherever x minus 2 equals 0, well, that happens exactly when x equals 2. So that's a boundary point. That's one of the boundaries on my table. But also, I need to find the roots, and the roots come from taking 5 over x minus 2 and setting it equal to 1. Well, now that I have equality, that's the only time I could fraction bust. I multiply both sides by x minus 2. I get that 5 equals x minus 2, or x equals 7. These are the values that I know important things happen at then, at 2 and at 7. And so I should put them in order from least to greatest when I make a table. Put 2 off to the left and then 7 followed by it, so that I know all the values to the left are all the values from negative infinity up till 2. All the values in between 2 and 7 are from 2 to 7 in interval notation. And then all of the intervals to the right of 7, or all the values to the right of 7 is the interval from 7 to infinity. So you should ask yourself what values you want to plug in. There are a ton of values to the left that you can plug in. You can plug in 1, you can plug in 0, you can plug in -1, you can plug in -2, anything to the left of 2. Well, I always choose 0 whenever category it's in. If it's here, I put 0. If it's here, I put 0, because 0 is the easiest for me to plug in. I can't choose 2, though. That's one of the boundary points. It's a divider. So maybe I choose something like 3 to the right of it. I could also choose 4 or 5 or 6. If I want to, I could choose a decimal, like 4.5. And then maybe to the right of 7, I choose 8. These are the 3 values that I want to test to see whether to the left of 2, my graph is above or below 1, to see in between the 2 if my graph is above or below 1, and to the right to see whether my graph is above or below 1. Again, I'm plugging them into the original now. I want to test these values. I just found these points for a second, and I'm going to use them in my table only. So now that I've found 2 and 7, I just rewrite my table, and I plug those values into the original inequality. Well, 5 over 0 minus 2, is that less than 1? Yeah, because -5 over 2 is less than 1. It works. But if I plug in 3, is 5 over 3 minus 2 less than 1? I don't think so, because 5 over 1 is just 5, and that is not less than 1. But then if I try 8, I know that 5 over 8 minus 2 is less than 1 because 5 over 6 is less than 1. So that works also. The intervals that work are negative infinity to 2 unioned with 7 to infinity. So then what this is saying graphically is that, if I had some imaginary sketch, then at 2 there's a vertical asymptote, and my graph is below 1 from 2 to negative infinity. So what's happening is maybe it does something like this. It never goes past 1. It might never go past 0, but that doesn't matter. It always stays below 1, and that's all that's important. Also, off to the right, maybe after 7, way over here at 7, that's where the graph is actually above, also again below the line, below 1. At 7 it becomes 1, but then it drops below 1 after that. So everywhere from the left of negative 2 and everywhere to the right of 7, my graph is below this imaginary line at 1. All right, so there's another one where you have a 0, maybe a few functions on top, but it's not that bad. If I write up 1, you'll see it's exactly the same thing. Like if I want you to solve x minus 4 over x minus 7 greater than or equal to 0, then I'm asking you where is this function greater than or equal to 0, but it's the same thing. First, I got to find the boundary points, which come from the vertical asymptotes. The vertical asymptote happens when the denominator, x minus 7, is equal to 0, so when x equals 7. The roots come from when I change x minus 4 over x minus 7 to an equation where it's equal to 0. I'm just changing the inequality to an equal sign for a second to find the roots. But in this case, when I fraction bust, I multiply both sides by x minus 7. And when I multiply 0 times x minus 7, I just get 0. So really, I'm just trying to find where x minus 4 is equal to 0. And I know that's x equals 4. This is a little bit different because it's allowed to equal 0. I know it equals 0 at 4. So when I make my table, my boundary points are 4 and 7. I'm putting them in order from least to greatest. And I'm telling you the interval is something from negative infinity to 4, but it's allowed to be 4 because of the original equation having a less than or equal to or a greater than or equal to. Because it's a less than or equal to, greater than or equal to, I should use a bracket at 4. But only at 4 because that's where it actually equals 0. What happens at 7 is I have a vertical asymptote. You should never include vertical asymptotes, so that always gets parentheses. That's the only real difference. And then now I can test something like 0, something like 5, and something like 8. I plug them back into this original inequality up here. So evaluating at 0 gives me that 0 minus 4 over 0 minus 7. I want to know if that's greater than or equal to 0. Well, negative 4 over negative 7, it does work. You get 4/7. That's greater than 0. Trying 5, 5 minus 4 over 5 minus 7, is that greater than or equal to 0? Well, 1 over negative 2 is not greater than or equal to 0. So the middle one doesn't work. But then trying in 8, 8 minus 4 over 8 minus 7, that's greater than or equal to 0 because 4 over 1 is greater than 0. So the answer then is from negative infinity to 4 with a bracket at 4, unioned with 7 to infinity. If you ever get confused about brackets versus parentheses, just go back to the problem. Because there's greater than or equal to, you should be thinking brackets everywhere. you never can put brackets on infinity, right? But also, you can't ever include vertical asymptotes, because what happens at 7 is you get 3 over 0, which is undefined. So you can't actually plug in 0, or I'm sorry, plug in 7. That gives you a 0 on bottom. That's why I also need a parenthesis at the vertical asymptote at 7. So 4 is the only number that I'm allowed to plug in. And again, those came from having the vertical asymptote in the roots. Roots are okay. Vertical asymptotes are not okay if the problem asks you for it. All right, so try the 2 that are on Math Excel. And if you have any problems, let me know.